Welcome everyone, my name is Maciej Skorski and I did this work when being a postdoc at the University of Luxembourg. The title of my talk is Tight Chernoff Balance under Limited Independence, and this is work accepted at Random 22. Let me briefly present the outline of my talk. I will start with an introduction into the topic. I will present then a key result. I will overview the techniques, comparing them to what was used in related work. I will discuss extra applications, and I will conclude the talk providing the list of references. Speaking of the motivation, let me recall that concentration bounds are essential to analysis of probabilistic algorithms. However, they are best understood in a somewhat restricted setup, namely when the components of the sum are independent, and this is well covered in the classical line of work contributed to by Bernstein, Chernoff, Hevding, Bennett. All those inequalities you have heard already. However, in practice, there is high demand for bounds that apply in more restricted setups when the components are dependent, such as those that appear when analyzing hash functions, which leads to the question, the major question I would like to answer in this talk, namely what more can be said about concentration properties of sums of k-wise independent terms. Essentially, the task is to develop tight concentration bounds under such a setup. That was a high-level problem statement. Now let me turn it into a mathematical problem. Formally, we consider the sum of k-wise independent random variables as our objective, and those components, those random variables, are subjected to the following constraints. First, we assume that the components are bounded. For example, they fit the range from -1 to 1, and second, that the total variance of the sum is bounded as constraint as well, and I use a constant here to denote this. The goal is to obtain best possible bounds on central moments of such sums under those constraints. So this is essentially an optimization problem where we optimize the objective understood as the central moment of this sum under the constraints as listed above. While we speak about central moments here, let me remind that by applying the well-established technique of Markov's inequality, we will be able to convert it into the concentration bounds, into the tile probabilities. So now it's time to discuss the result itself in more detail, but before doing that, let me quickly overview the related work. The topic is not new, and I'm not the first person touching on that. I should, in first place, credit the more general inequalities that are able to provide us with concentration bounds, assuming that we know something about the dependency structure among the terms. And such works were pioneered by Suen and Jansson. You can follow the references to get more details. However, in our case, in the specific constraint setup that I already discussed, the state of the art is held by the two influential works. The first is the paper by Schmidt et al., and the second is the one from by Bellare and Trompel. Both those works resort to direct moment estimates rather than employing something established for the sake of squeezing the maximal performance, the maximal accuracy. Still, there is a gap to address, and addressing this gap is the contribution of my paper. The gap follows from the fact that first, the prior works don't cover all parameter regimes, and second, they are not uniformly optimal. They are only optimal under certain cases. And this is essentially my major selling point. In this work, I'm going to solve this problem completely by providing the sharp formula that is uniformly optimal. Before showing the formula, just three definitions. First, we speak about k-wise independence when any k-element subset of our collection of random variables is fully independent. And second definition is just a reminder on how the LP norms are defined in terms of the moments. Basically, to get the norm of order D, we need to compute the absolute moment of order D and then apply the square root of order D to normalize. Finally, the Bernoulli distribution is a binary random variable which takes the value 1 with probability P. This P is a parameter, is the distribution parameter. Now we are fully ready to state the main result. The main result is the formula for the maximal moment of a sum of k-wise independent terms, provided that they fulfill the constraints that we already mentioned. The first constraint is the boundedness, the interval -1, 1, and the second constraint is the assumption that the total variance is constant, equals a certain constant term, or it is at most a certain constant term. Under such a setup, we obtain a formula which gives the sharp asymptotics for the norm of order D for essentially all orders up to the k. The k same as in the k-wise independence assumption. So all moments of lower order we have under control, and we have a complete understanding what are their maximal worst case values. Let me mention briefly that higher order moments cannot be computed under the k-wise independence assumption, so we are essentially squeezing everything that can be said in such a case. The maximal value, that might not be that surprising, but it is also a part of the contribution to prove it rigorously, is achieved when all the components are essentially binary random variables and have or the random variables taking 3 values, actually differences of 2 independent Bernoulli distributions, and are of same variance. So the homogenic case makes this formula most dispersed, makes the moment most dispersed. Let me briefly overview the proof techniques. This paper introduced a novel concept by applying the algebraic methods. Essentially, I expand the formula that arises from the central moment and analyze it, reduce it by using symmetric polynomials heavily and the theory of symmetric functions and inequalities, related inequalities. This is in contrast to prior work where we have seen combinatorial arguments to count patterns that appear in the expanded sum, and also direct analytical moments, namely computing and estimating integrals that arise from computing the moments by the integral formulas. Being more specific, how do we attack the problem with symmetric polynomials? We take this sum, we expand its dth power and organize as a symmetric polynomial. Then under the boundedness constraint, we reduce it further to elementary polynomials. I'm providing a small example here, but essentially the idea is to use the boundedness assumption to eliminate non-homogenic terms, or rather to replace the non-homogenic terms with homogenic one. After this operation, which is sharp for the before mentioned worst case, we are left with elementary polynomials, and those elementary polynomials can be further analyzed by the so-called Maclaurin's inequalities, which essentially leads to the conclusion that the worst case is when those random variables are of equal variance. It remains then to work out the missing details, that is to develop the exact formulas, and this is where the paper obtains the 3 branches as opposed to 2 branches from prior work. Speaking of applications of independent interest, let me make those 2 points. First, as a byproduct of this approach, I obtained uniformly sharp bounds on the binomial moments. And second, in the paper I give a detailed comparison of prior works, Schmidt and Bellare-Rompel bounds. This might be of interest to those of you who wonder which bound is actually better, and where in my paper I simplified those bounds a bit to make them more comparable. For the details, please refer to the full paper. And now let me jump to the conclusion. An accurate overview, in my opinion, is that this work established tight Chernoff bounds under k-wise independence with 3-branch formula, which is somewhat surprising but completes the line of work that Bellare and Schmidt et al. Started. The new proof technique introduced here is the utilization of symmetric polynomials and essentially algebra, which might be of interest to some of you. Essentially, this way we outperform analytical and combinatorial estimates. Finally, contribution of independent interest is the bound uniformly optimal bound on binomial moments. Finally, I would like to acknowledge the support of my research grant from the University of Luxembourg, and also to thank the reviewers of Random 22 who shared with me many valuable comments on the prior version of this work submitted to the conference. I would like to thank those anonymous reviews for that. I conclude with the reference slides, and if you have any questions, please feel free to reach out to me. The email is shared in the full paper. You can also find those slides online at my ResearchGate profile. Thank you.